Hey guys, welcome to chapter 2. So what we have today is we're going to review a little bit of trig functions. We have a new vocab word called cofunctions, and we're actually going to introduce the unit circle. So just wanted to draw your attention to this chart here. Remember, these are the same ratios that we used last chapter, and they're the same ratios they're going to be moving forward. But just a basic geometry review here, what I want to do first is it asks find the 6 trig ratios for a triangle with sides 7, 24, 25. So what I'm going to do first is actually draw a triangle. And the thing you have to remember is, do you know which side is the hypotenuse? Always the biggest side, right? Hypotenuse is always the biggest. So that means the 25 goes here. The 7 and the 24 doesn't matter. I'll just make it look a little bit to scale there, put the short side as the 7. So they didn't give us a theta, so I'm just going to shove it right here. You could still do the 6 trig ratios if the theta was up here, but this problem wasn't specific, so I'm going to put it right here, and I'm going to write out the 6 trig functions. So here's what those look like. Just basic review. Remember, we're using y and r and x and r. I did not draw my triangle on a coordinate plane. So in this case, I'm just using opposite, adjacent, hypotenuse, whatever. But just remember, what's important here is that we have reciprocal functions. So whatever the sine is, the reciprocal of that is the cosecant. Same thing with cosine and secant. Same thing with tangent and cotangent. So keep those in mind. And now I'm going to give you a definition of a really important word called cofunctions. All right, so here's our definition. They are pairs of functions, so 2 functions that go together, and their angles are complements. And so that, remember the word from geometry, complements, like complementary, that means that they add up to 90. Okay, and so what they are, and this is actually kind of cool, not sure if you've put this together yet, but they are in pairs of cos, if you will. So sine, there is also a cosine. And for tangent, there is a cotangent. And for secant, there is a cosecant. So not sure if you have been wondering why they're named this so far. That's because they are cofunctions. So don't get that confused with the reciprocals like we've talked about already in chapter 1. So these are different than sine and cosecant being reciprocals. Don't get that part confused. In this case, they are cofunctions, and that means that their angles are complements. So what that means is that the sine of A is equivalent to the cosine of 90 minus A. They're equivalent. Same thing with tangent here. That's the same as the cotangent of 90 minus A. And we also can do secant. Cosecant of 90 minus A. And make a little note, same thing for vice versa. What I mean by that is that cosecant is the same as secant of 90 minus A. So cosecant of A, I mean. That is that. Let's actually look at how these are going to be done. So write each function in terms of its cofunction. So cosine of 54 is the same thing as the sine of 90 minus 54. So it equals the sine of 36. Same thing for the secant one over here. So that's going to equal the cosecant of 90 minus that whole thing. You can probably see where I'm going with this. Make sure you actually use parentheses because a lot of people forget to distribute that negative sign. So just be careful about that when you are writing the cofunctions. So that means it's 90 minus theta minus 17. Which gives us cosecant of 90 minus 17 is 73 minus theta. So these are equivalent. They're cofunctions. All you have to do is subtract the angle from 90. This is equivalent. Okay? In order to find a solution for the equation, it's going to be the same kind of thing. What I want to do is rewrite these. One of them is cosine and one of them is sine. We've alluded to this a little bit in the past with the reciprocal functions, but we're going to use cofunctions here. So I'm going to rewrite cosine of theta minus 4 as sine of 90 minus theta plus 4. And I'm going to distribute my minus sign here. Be really careful about that. Common mistakes. 90 minus theta minus 4, that means that sine of 86 minus theta is equal to, just drop this thing straight down. We haven't touched the right side at all. 3 theta plus 2. And remember, now that we have a sign on each side, these functions are equal. That means that their quantities, what's in the parentheses, are equal. So you can just set those equal to each other and solve. 86 minus theta equals 3 theta plus 2. That means that 4 theta equals 84. Theta equals 21. Basic algebra from there. All right, so this next one is a tiny bit different. It's actually a review problem. But I want to point out here that this is what I was talking about. Don't get confused with the cofunctions versus reciprocals. So cosine's cofunction is sine. So if we rewrote this, we would have sine and secant. Secant's cofunction is cosecant. So if we rewrote this using the 90 minus the angle, we would have a cosine and a cosecant. So don't forget the reciprocal properties that we have already used in the past. So since rewriting using cofunctions wouldn't help me in this problem, what I'm going to do is use reciprocals, and I'm going to change this secant into cosine so that at least I have all cosine functions in my problem. So I'm going to leave the cosine 3 theta plus 1, but all I did is I rewrote the secant as 1 over the cosine. Don't forget the reciprocal functions. So we've done a problem kind of like this in the past. What you can do is make this into one fraction by just doing top times top, and there's really a 1 down here times the bottom. So what I'm going to do is write cosine of 3 theta plus 1 on the top, and cosine of 5 theta minus 17 on the bottom equals 1. Cross multiply. That means that cosine of 3 theta plus 1 equals cosine of 5 theta minus 17. Now again, we have cosine on each side. That means that you can just set the quantities equal to each other. So when you do that, I'm running out of room, come up here. 3 theta plus 1 equals 5 theta minus 17. Combine like terms, theta equals 9. All right, what I want to do, you guys, is save this bottom part of the first page for class. I want to talk about this and those two examples in class and have that discussion so I can demonstrate something for you. So go ahead and flip the page, and I want you to focus for a second on these geometry review things. So do you remember 30, 60, 90 triangles and also 45, 45, 90 triangles? And there's like relationships between the sides and all that kind of stuff. I want to point out a few things about the relationships here. I'm going to zoom in on our 30, 60, 90 triangle. Just to review, the 30, 60, 90 has to do with the angles. Same thing over here with 45, 45, 90. But what I want to point out here is that the short side here is half of the hypotenuse. Here's the short side, here's the hypotenuse. So this is something to note. If you want to go from the short side to the hypotenuse, you double it. And then same thing, if you want to go from the hypotenuse to the short side, the relationship there is you divide it in half. So those two sides always have that relationship in a 30, 60, 90 triangle. The hypotenuse is double the short side. Keep in mind that this short side is always across from the smallest angle. So if you're not very good at drawing a triangle like to scale, make sure that you always have your short side across from your 30-degree angle. Okay, there's also a relationship between the short side and the long side. So here's the short side and here's the long side. And the relationship there is you multiply by radical 3. Okay, and same thing, if you had the long side and you wanted the short side, you would divide by radical 3. And there's a similar relationship over here for the 45, 45, 90s. You'll first of all notice that this is an isosceles triangle, so don't forget that like this side always equals this side, so that's a little bit more simple for the 45, 45, 90 triangle. But if you have one of the sides and you want to figure out what the hypotenuse is, you multiply by radical 2. I like to remember the 2 because we have two sides that equal each other. The 30, 60, 90 triangle has a radical 3 in it because it has a 30-degree angle. So think the 2's go together. The 2 has two equal sides. The radical 3 is the one with a 30-degree angle. Hopefully you remember a little bit about this from geometry, because this is the basis of the unit circle. And then just remember, if you have the hypotenuse and you want to figure out one of the sides, you just divide by radical 2 and rationalize. That's why the radicals look like that. Okay, but anyways, the good news is that there's only 2 special triangles. And the awesome part is that we are going to use these 2 special triangles, this one and this one, with these side lengths actually, for the entire unit circle. So if you can memorize, I wrote memorize these here. If you can memorize these triangles and probably write them at the top of your test or quiz or whatever it is you're working on, then you have the entire unit circle, all the answers, everything. You just have to be good at reflecting it, turning it over, flipping it upside down. So do you think you could still put a 1 on the hypotenuse, a 1/2 on the short side, and a radical 3/2 on the long side if I drew the triangle facing like so? That's what I want you to think about. If I flipped this triangle upside down, could you still put a 1 on the hypotenuse and the radical 2's on the other 2 on the legs? That is what I want you to like think about and start concentrating on. But since you have these 2 triangles up here, what I want you to do is pause the video and fill out the table, okay? And then I'm gonna fill it out also, and then you can just check your answers with mine. So pause the video, fill out these with the chart regarding this triangle and this triangle. Go. All right, here is the whole chart. Hopefully you nailed all of these. The thing to think about is that these are not on a coordinate axis yet. So the X's and the Y's and the R's might have freaked you out a little bit. It's okay to go back to opposite adjacent hypotenuse. It's all the same thing, and it should all work out for you. If these triangles were on the coordinate axis, the XY axis, then you would have to take into consideration which one's X, which one's Y, whatever. Okay, I did want to point out for the tangent of this one, I just wanted to show the work for it. So tangent is opposite over adjacent. So it is the 1/2 divided by the radical 3/2, which is here. And so remember how to divide fractions. You keep the numerator and you flip the denominator and it turns into multiplication. And then your 2's cancel on each fraction, and you end up with 1 over radical 3, which rationalizes to radical 3/3. So just be careful about that. I wanted to show that algebra in case you got tripped up on that. Similar work for the secant question. And I also want you to see if you can come up with some patterns involving the sine of 30 and the sine of 60. And same thing for cosine and same thing for tangent. Okay? I want to show you how this becomes the unit circle. So I actually dare you to Google image the unit circle, because you're going to maybe be a little bit overwhelmed, but I want to show you that the unit circle comes from this chart and those 2 triangles up here. I'm going to draw those triangles onto the circle, and remember it's called the unit circle because the radius of the circle is always 1. So no matter where I draw my radius in, the hypotenuse there is going to be 1. So this is my 30-degree angle. If I make a triangle out of it, could you put the 1 on the hypotenuse? Well, it's already there. We already knew that the radius of the unit circle was 1. But remember what the short side is? It's 1/2. And remember what the long side is? Radical 3/2. So can you then tell me what ordered pair goes here? So this side was radical 3/2, so that's the X. And this side was 1/2, so that's the Y. Okay, so similarly, we have a 45-degree angle here, so that's the other special triangle. Remember that the radius is always 1, and if I drop this down, do you remember what each of these sides is with a radius of 1? Could you tell me what this ordered pair is? So remember we went right, radical 2/2, it's above on that triangle, and up, radical 2/2, those sides are equal. And then last but not least, we have a 60-degree angle also. Remember the radius is always 1, that's what I'm drawing in right now, really thick and heavy, that's the hypotenuse. If I drop my triangle down here, could you tell me what this ordered pair is? So for this triangle, it's a 60-degree angle right here. And so that means the triangle is flipped a little bit. This is my 1/2, my short side, and this is my radical 3 over 2. So I went right 1/2 and I went up radical 3 over 2. And then we've already talked about how this point here is 1, 0, that's 0 degrees. And this point here is 0, 1, that's 90 degrees. So we have just done the first quadrant of the unit circle. And in class tomorrow, we're going to talk about reflecting it and everything else. But I want to remind you that they're all just special triangles. And all you have to do is remember this triangle and this one and be able to place it on the grid. Okay? That's all. Thanks for watching. Bring your questions to class, and I'll see you tomorrow.